One of the best ways to understand how capacitors work would be to test an electronic circuit using a simulator. So in this case, we're focusing on RC circuits. So circuits made up of some resistor and a capacitor. And what we're interested to see is how we can charge a capacitor and how we can discharge a capacitor. And what we will be doing and what we will show in this video is the use of Multisim, and in particular MultisimLive. Multisim comes from National Instrument, NI, and MultisimLive is a web-based version of Multisim, and it's in fact available free of charge for anyone to use. So you do not need to have the license to do that, and we'll show how this is done. Registering with Multisim is straightforward and easy to do. You simply need to go to multisim.com. Once you're there, you could just press on sign up for free, put in your email, and then a confirmation will be sent to your email. You confirm that, and then you simply need to log in and then begin the use of the simulator. So once you finish registering to Multisim, you go again to the website, you log in with your credentials, and you launch a circuit. And this is the interface that you will get once you have the simulator, the web-based simulation screen that you will have. You could you'll have that. You could expand it so it will take the entire screen, so that it's easier for you to do to build the circuit that you want. So some of the things that we will use, particularly for this course, but also for advanced courses, so you have different options on the left side on this menu. So the ones that we will mainly focus on is on the probes that we will use for analysis. So this is essentially the equivalent of a DMM, of a digital multimeter. So you have a voltage probe, you have a current probe, you have a voltage reference, you have a voltage current probe as well. Instead of having two, you could just put one probe that will get you both voltage and current. You have the ground that we will use for a circuit when you build it. It's always a good practice to include a ground in your circuit, because in that case you would not need to include the one of the polarity of your probe. You simply put the positive side, and for the negative, automatically Multisim will measure it with respect to the ground. And if that's not your case, you want to create a potential difference, well, you need to put the negative side of your probe, and it's very straightforward to do with Multisim. And also, of course, we have the sources that we will need to use. So if we're talking about a direct current, a DC voltage source, you could pick it up from here. A DC current source, you could also get it from here. An AC voltage, an AC current, you could also get it from here. You need to set the amplitude and the frequency for the ACs. And for the DC, you simply need to put the proper voltage or the proper constant current for that. As for the components that we will need to use, well, we will mainly focus on passive components. So primarily resistors and capacitors. We won't see inductors and transformers in this course, but you will see that perhaps in other courses, and this simulator will be useful for you. So we'll just focus on these two. And in fact, today for this demonstration, I'll be using resistors and capacitors from the passive components. So perhaps I should just quickly highlight what's the difference between passive and active components. Passive components are components that are incapable of controlling current by means of another electrical signal. So like we said, resistors, capacitors, inductors, and things of the sort. And then active components are components that you could control current by means of another electrical signal. So some examples of active components are diodes, transistors, and ICs, integrated circuit, and others. So anyways, you have this here. You have the probe, you have the ground, you have the sources, you have the passive components. And we also, for this demonstration, for this simulation, you could grab the proper switch that we will need to use to basically charge a capacitor and then discharge. And to trigger this, we'll need to use a particular switch. And the one that we will use will be the SPDT switch, the single pole double throw switch. And we'll show you how this is done in here. So in principle, what we are interested to do is we want to see how we can charge the capacitor that you see here. And when we do this charging of the capacitor, I mean, ultimately the goal is essentially just to store energy in this capacitor. And you can think of a capacitor kind of analogous to a battery. A battery has energy inside of it, and when used in some consumer electronic device, it releases that energy, and it's able to kind of allow us to use the different electronic devices by using the energy that is stored in the battery. Now, the key difference between a battery and a capacitor, among other things, is the way that energy is created and stored. So, in a battery, energy is essentially stored in it using some chemical reaction. With a battery, with a capacitor rather, energy is essentially stored inside a capacitor electrically, and this is how this is done. So, in principle, you have some source, in this case a DC source, so a direct current source that is connected to some resistive element, and this resistor is connected to the capacitor, and that's how you are able to charge your capacitor. So if the switch is closed here, the capacitor, which we assume is initially discharged, so if I take a DMM and measure the voltage across the capacitor, it should be 0 volts. Now that I close the switch, it should start, so current will start flowing. Current will start flowing in this way. And then as the current starts flowing, buildup of charge will happen on the plates of the capacitor. And then eventually the capacitor may reach the maximum value that we have here. So if the source is, I don't know, let's say if it's 5 volts, then in that case, the capacitor will eventually reach 5 volts if we give it enough time to charge. And how long it takes to charge, all that is really dependent on the value of the resistance and also the value of the capacitance. And in fact, since we're talking about capacitance, you could determine, I mean, fundamentally, the capacitance of a capacitor is defined by this equation. So you could find the capacitance of a capacitor using epsilon naught, epsilon r, A over D. So if you have two thin sheets of metallic plates, D is the distance between the two plates. So if you have two plates like this, so this is a very rough drawing of what a capacitor should essentially look like. So there are two carbon copy thin sheets of plates that we have, and D would be the gap between these two plates. So it would be this. This would be the D that you have. It's measured in meters. A is the area of each of the thin plates. So A is the area of the thin plates. And epsilon R in fact, is the relative permittivity of a dielectric that you use. So where do you put the dielectric? Is you put it between the thin sheets of plates. So this could be, for example, it could be air. So if you use air, then the relative permittivity will equal to 1. And by the way, the relative permittivity has no units. So the units of this one is meter squared. The units of this one is simply meter. This, no units. So no units. And the permittivity in free space, well, this has it has the unit of farad per meter. Okay. So let me just say the different epsilon R values. So for air, it would be 1. What else do we have? For wood, let's say if you put a piece of dry wood between the two thin sheets of metal, well, in that case, it's somewhere between 3 to 4. 3 to 4. If we put, for example, rubber, well, a rubber should have a relative permittivity of 7. And you could go all the way to for different dielectric that you could put between the thin sheets of metallic plates. But the one that is very popular is ceramic. So if we use ceramic, well, a ceramic has a relative permittivity of 1200, so 1200. And if you notice that it goes up. And if you notice some of the characteristics here, so if the area the area of the metallic plate goes up, well, what this means is that the capacitance of the capacitor will go up. If the distance, the gap between the two plates will let's just say will go up, well, in that case, what happens is that the capacitance will go down, right? They're inversely proportional, whereas area is directly proportional. And if the type of dielectric or insulator that you put between the plates, the epsilon r, well, if this one goes up, well, it's also directly proportional, so capacitance will also go up. So there's a very nice knobs that you could do if you design your own capacitor, is to modify the area of the plates. You could change the distance between the plates, and you could also change the permittivity. This is just the physical background of how capacitors work. But now I think we could just erase all this. This is just a very quick introduction to kind of get us started with how capacitors work. I'm going to just erase it so we could focus more on the electrical engineering part of how capacitors work, and not really on the physical part of what people in physics will do to understand how capacitors work. But nonetheless, I hope this kind of quick introduction gave you a sense of how a capacitor is, what it is, and how you put it all together. So let's say we want to charge. Like we said, we would close the switch in this direction. Current will start flowing until this capacitor is fully charged. When it's fully charged, current will reaches zero, and that's it. The circuit is no longer operating. The current will be zero. If you want then to discharge the capacitor, what you could do is you could then change the switch. Like you could, in that case, you could put the switch on this side. So if you put the switch on this side, what's going to happen is all the charge that now you have in here, let's assume if it was 5 volts, if it was less than 5 volts, you didn't give it enough time to charge, that's fine. You could have maybe charged it until 4 volts or 2.5 or 2.3 or whatever number it is. That's fine. You could stop it whenever you're happy with how much charge you have in the capacitor. Once you have that, you could leave it as such and just not use the switch. But you could also discharge this, the charge that you have in the capacitor, the voltages that you have in the capacitor. So the way that you discharge it is by using this switch. So you close it on this side, and then current will start flowing. Current will start flowing until it dissipates all the charge that it has through this resistor, and that's how you discharge a capacitor. And then you need to have a certain amount of time that this circuit should be closed in this direction until the capacitor is fully discharged. How much time do you need to discharge that? Well, we'll talk about that on the next slide. So that's in principle the way that you could charge a capacitor and you could discharge a capacitor. So this is a view of how to do this with only one resistor and one capacitor. So I hope you kind of get a sense of how this is so basic and how you could do it very quickly. You could also charge and discharge a capacitor with two resistors. So in this case, in this schematic, what I wanted to show is that you could in fact charge a capacitor with one resistor. So I call it RC for charge and RD for discharge. So if you want to charge, you would put it, you close it like this, and then this is the resistor used to charge your capacitor. And when you want to discharge, well, in that case, you could put it, you could use the other switch. You could put the switch on this direction, and this is how you discharge. And what's interesting is that these values, let's assume they're not the same. They're not the same. So the rate, the speed at which you can charge a capacitor and the speed at which you can discharge a capacitor will be different. And the way that you could measure the speed at which you could charge a capacitor and discharge is using the so-called time constant of the RC circuit. The time constant is very easy to get. So in this case, we're charging and discharging with the same resistor. So the time constant for charging, the time constant for discharging is the same. And the way that you do it is you simply take the value that you have for resistance, you take the value that you have for capacitance, and you multiply them together. And this should, in principle, give you a result in seconds. So just S in seconds, that's the unit for tau. Here, the unit for resistance should be in ohms. So if you have it in kilo, just bring it down to ohms. And here, the units for capacitance should be in farad. So if you have it in nanofarad or microfarad or picofarad, just bring it down to farad, multiply them together, and the result that you get will be in seconds. And then you can put it in engineering notation to have it in the proper way that we've seen before. So in here, the time constant is critical to get. But as you see, you just get the same time constant for both charging and discharging. Whereas if you are charging and discharging using different resistors, the rate for charging and discharging will be different because it will depend on what's the value that you have for RC and what's the value that you have for RD. So in this case, we are charging using RC, so it will be a certain rate, and we're discharging the capacitor using RD, so it's a different value. Let's assume RC does not equal to RD, right? So the charging and discharging will be at a different rate. And we'll see an example of this. In fact, this is the one that I will use to show you the simulation today, this one here, so that you can see how you could charge and discharge going at a different, not necessarily the same rate. But if you do want it to go on the same rate, well, use this circuit. It's also much easier to do. But like I said, the one that we will do today will be this one here with two different resistors. I hope this makes sense. Now that we have some understanding of how charging of a capacitor and discharging of a capacitor happens, it's interesting to visually see how this evolves graphically. So using graphics and some formulas. So in this case, what you have on the y-axis is voltage. So this is the voltage across the capacitor. And what you have on the x-axis is time. So this is time in, so the default measure is seconds, but if everything is in milliseconds, well, time can also be in milliseconds. And here the default way of measuring voltage is in volts. So as you charge your capacitor, notice that the voltage starts going all the way to the maximum value. So when it reaches maximum value, it means it reaches 100% of charging. Now, maximum value could be something that you decide what it is. So if you let it, you give it enough time to charge, the maximum value will be the value of your DC source. But if you stop charging at some point, the maximum value is wherever you decided to stop, right? I mean, that is your maximum value. So you have to be careful why this is not always the value of the source. It depends on what we mean by maximum value. It's when you decide to stop charging the capacitor, this is your maximum value. So this is how the curve looks like. And it grows gradually until it reaches the maximum value. And what's interesting to notice is that maximum value, or sometimes we refer to it as 99% charge, which for all practical purposes is fully charged, reaches at 5 tau. So you know tau already. Tau is the time constant. So tau is equal to R times C. And if you multiply it by 5, well, this gives you 99% of full charge. In fact, it's not entirely 5, it's 4.6, but 5 is what we typically like to remember for how much time it takes to charge a capacitor. It's easier to remember rather than 4.6, and that's how we get it. Now, in terms of current, like I said earlier, as you start charging the capacitor, current is at its peakest value. So how do you measure maximum current? Well, you take the maximum voltage, you divide it by the resistance. This gives you the maximum current. This comes from Ohm's law. And then as you start building charge on the capacitor, current gradually diminishes all the way until it dies out, until it goes to zero. So when you have fully charged capacitor, the current goes to zero. And when you are not in full charge, you're beginning to charge, the current is at its maximum value. So this is something that is interesting to notice, is that at maximum charging, which is here on the red curve, the current reaches zero. And when you begin charging, your voltage is zero, but your current is at its maximum value. Maximum value, which we said is obtained using Ohm's law. So anyways, this is it. Now, these two plots can be represented analytically. using these equations. So this is the first equation, is the equation that is used for charging a capacitor. So this is the voltage across a capacitor as it starts charging. So this is the equation. And this is the equation for the current that is flowing through the capacitor as the capacitor starts charging. So notice how it is. This one here for the current, it's gradually dying. It's going towards zero, and for the voltage, it's going up until it reaches a maximum value. So one is growing and one is diminishing. So you can see that visually and also with the equations. So in fact, we could verify some of these values. So maybe we're curious to realize, like, okay, so how do they get this 86% charge at 2 tau? Well, you could use the equation here. You could use these equations. Let's say we want to find how did they get 86%. Well, we know that we could just test it. We could just plug in 4. So let me just show you how this is done. So we take the equation. We say that we're curious to know what is the voltage at t equals to 2 tau. Okay, t equals to 2 tau. This is what it is. What is the voltage? This is the question. What is V of the capacitor at t equals to 2 tau? Okay, this is what we're after. And just so you know, again, so we have a capacitor. Okay, maybe I should be a bit more precise on how to draw the capacitor. So this is the capacitor that we have. And in fact, I should mention that there are two symbols for capacitors. So we could have a capacitor like this, a polarized capacitor that looks something like this. If you see something like this, so it's curved at the bottom and straight line on top, it means this is the plus, this is the minus. Whereas if you see two straight lines, it's non-polarized, so you could decide which side is plus, which side is minus. Let's assume this is the plus side, this is the minus side, and it's not polarized. So this is just to know in terms of notations of the schematic. So let me erase the polarized one, but I hope you now know how the capacitors come in different flavors. And we want to know the voltage across this capacitor. So this is it, VCT. This is the voltage across the capacitor, so it's this one here. And the current through the capacitor is ICT, and this is the current through the capacitor. And of course, the capacitor is here, the unit for capacitor. So this is in farad. The current is in amps, and the voltage is in volts. So I mean, amps, but it could be milliamps. It depends on what we get for the value for it. So this is what we're getting. So we want to know what is the voltage. What is the voltage at 2 tau? So when time is 2 times tau, and let's not forget what tau is. Tau is the time constant. So how do you get tau? Like we said earlier, it's just R times C. So if you have an RC circuit, just when you're trying to charge, just look at the circuit that you have. So we have some circuit, we have some resistor, and we have some capacitor. We start charging, we close the switch. So multiply R and C, and this gets you your tau. So let's just put it in the equation. So if we put it in the equation, well, what do we have? We have V max, okay, 1 minus E to minus, well, T is 2 tau, over RC, and we said RC is essentially just tau. I mean, in the equation here, I typed it with RC, but this is in fact just tau, right? This is just tau. And tau cancel, so what do we have? Well, we have Vmax, 1 minus E to the minus 2. Okay, so if we take our calculator, and I'm going to do this live right now with you, so let's just let me do this. So E to the minus 2, we put a minus in front of this, we add 1 to it, and we essentially get roughly 0.865 Vmax. So what this means is that it is roughly 86%, 86 mile, and in reality it's 86.5% that we get of Vmax. So it is 86% of the maximum value, okay? Maximum value, and this is how we get this 86% that you see here. Now, if you're curious, well, we might say, well, how do they get 37% for current? Well, you do the same thing. You do the same thing, but now let's erase, so we have more space, and I'll show you how to do that using the equation for the current, and you get the same idea of how we got this. So let's erase. So we want to know how we obtained this 37%. Well, the way that we got the 37% is we do this. We say at tau, we're curious to know what is the current. Let me just use a small I. What is the current of the capacitor when time is equal to tau? And tau, we know what it is. It is simply RC. Well, it is equal to I max, maximum current. The maximum current is obtained from Vmax over R, right? So Vmax is the maximum voltage where I decide to stop charging the capacitor, and R is just this value. And then I simply do e to the minus tau over tau. Well, tau and tau cancels. Well, this leaves me with I max e to the minus 1. And we could again try it with a calculator. So we could just put e to the minus 1. And this is equal to 0.368. So roughly 0.368 I max. Or if you will, it is 37% of the maximum current. 37% of the maximum current. Alternatively, what we could also do is, well, we could say, well, I want to know when I will reach, I don't know, this value, when I will reach 90% charge. When does 90% charge happen? At what value does this happen? Well, we could also use the equation. So again, it's just a way of getting familiar with these equations and learning how to use these equations. So let's just try it. When will we reach 90% charge? So let's just try the equation. Let's see how we can make sense of this. So if I want to reach 90% charge, it means that I want my V of t. We don't know what this t is. Let's call it t naught. T naught is equal to 90% charge. So I could write it as 0.9 Vmax, right? Equals to Vmax, and then I could do 1 minus E minus T over RC. Okay, and in fact, instead of writing RC, let me just replace it and just write tau in here. So over tau. Okay, so now I could do some simplification. So Vmax and Vmax is canceled. So now I have 0.9 equals to 1 minus e to the minus t over tau. I'm looking for t. We called it t naught, so let's just call t naught here as well. Let's call it t naught here. T naught is this. At what time will I reach 90% charge? So let's do that. So essentially, we want to isolate for t naught. So what I'll do is I'm going to move this part to the left side and move the 0.9 to the right side. So just kind of rearranging things. So I have minus t naught over tau on this side, and I have 1 minus 0.9 on this side. 1 minus 0.9, well, this gives me 0.1. And now what I have is I could do ln on both sides. I could take the natural log on both sides. So if I take the ln on this side, ln of this, and if you will, ln of this, well, I'm going to just erase so I have more space, and then we'll continue. So just bear with me as I make some space to work. Okay, so now let's continue the work that we have. So we do ln of 1 minus 0.9, so this becomes ln of 0.1. So let's just rewrite it here. So ln of this becomes minus t naught over tau, which is equal to ln of 1 over 10, okay? And ln of 1 over 10, well, I could just also write it as ln of 10 to the minus 1, if you will, and I could also write it as minus ln of 10. Just another way of just kind of seeing the relationship of natural log here. And let me just now isolate gradually for t naught. Therefore, the minuses can be canceled, so we could cancel the minuses. So let's cancel this minus, let's cancel this minus. So we'll have t naught equal to tau ln of 10. And if you do this, so let's just try this. Let's do ln of 10. This gives us 2.3, roughly 2.30 tau. So 2.30 tau. This is where at this point I would get 90% charge. And if you look at it on the graph, it kind of makes sense. It's somewhere between 2 and 3. So at 90% charge, so it's maybe somewhere here, so maybe it's not fully up to scale. We expect to get 90% charge at 2.3 tau. So how do you know specifically what this value is? Well, just enter the value of R for tau. Just enter the value. Just get it through by multiplying R and C. Multiply by 2.3, and this should get you the value at t naught. So this is just a way of how to manipulate and to use these equations to find whatever you're trying to find. So let me just erase so we have more space to show you the rest of what I want to show you. Now, in terms of discharging, I'm going to show you the related plots and the equations that we could get. So just bear with me as I clean this page a bit. So for discharging, this is what we have. We have this plot. So when you want to discharge, this is what you get. And in fact, what's interesting to notice here is that when you're trying to discharge a capacitor, both of the plots, the voltage and the current, are both unwinding, are both kind of converging towards zero. And the related equations for them are this. So for the current, so the equation for current is in fact the same for both cases. When you're trying to charge, this is the equation for it. The curve is going towards zero. And when you're trying to discharge, it's the same thing. It's still going towards zero. But what changes is this one here. The equation for discharging for voltage, it becomes this. So when you discharge, well, how is the circuit looking? Well, this is how it looks like. You have some resistor for discharging, or if we just use the same one, let's just call it R, and we connect it to a capacitor, and that's it. We just connect these two together. If this is positively charged here and negatively charged here, this is the capacitor, well, current will flow this way. It will gradually dissipate. It will empty up all the voltage that it has in the capacitor until it's fully discharged. And this is how you can see it using these two equations. So I hope this allows you to see how we can charge and discharge effectively. Now, I just would like to add one more thing before we move on to the next topic and eventually to the simulation. So there's a number that we, like I mentioned earlier, what we like to always remember when we talk about charging and discharging of a capacitor, and it's 5 tau. 5 tau is a number that you'll see this mentioned in books and on different documentations. 5 tau. So 5 tau is the time that we could say we can estimate that the capacitor is fully charged. So it's not fully charged, it's 99% charged. Again, 5 tau when we could estimate that the capacitor is fully discharged. So 5 tau is this key number that we like to know. And in fact, well, you might say, well, why is it 5 tau? Why is it not at 100%? Well, if you check the equation, it would not work with 100%. If you want to reach 100% charge, so in other words, if VC equals to some T and it reaches 100% charge, so 100% charge, Well, what is 100% charge? 100% charge is in fact equals to Vmax. Vmax. And we're saying this should equal to Vmax. Let's just write it in here. Vmax over 1 multiplied by 1 minus e to the minus t over tau. Well, if I cancel the Vmax on both sides, the left and the right, what I'll end up getting is I'll have a 1 equals to 1 minus e to the minus t over tau. And then the 1 and 1 is canceled, and I'll end up with 0 equals to minus e to the minus t over tau. And this will get me into some trouble here because I could get rid of the minus, and then what do I have? I will have e to the minus t over tau equals to 0. And then if I want to find for t, what I could do is I could use the natural log like we've done before. We'd use the natural log. Let me just make some space. And let's see how this will end up happening. So if I use the natural log, well, I'll get ln of e to the minus t over tau, and I take ln of 0. And I don't know if you recall how the natural log is. It's something like this. And as you go to 0, it shoots up to minus infinity. Shoots up to minus infinity. So in reality, this becomes minus infinity. And so if I mean, maybe from calculus, or you could know this, or even just from just high school math, you'll know that as ln goes close to 0, it goes to minus infinity, and this becomes minus t over tau equals to minus infinity. And so t will in fact be at infinity. When t is equal to infinity, this is where you will have full charge. And so this is not very practical for electrical engineers. So in that case, that's why we always use 99% charge, 99%, or rather 1% charge to mean that. So for us, when we see 99% charge, for us, this is considered fully charged, fully charged. And when we see a 1% charge, for us, this is considered fully discharged. Fully discharged, because otherwise it would not make sense with the equation. We'll get infinity. Only at infinity we get fully charged or fully discharged. Doesn't make sense. So that's why we will always use the 99% and the 1%. And if you do that, in fact, if you do that, let's just also, since we're talking on it, if you do that, you'll see that why we get this 5 tau. Let me just prove to you why this 5 tau is obtained, and then we could just move on to simulation after all this nice theoretical background. So this 5 tau is obtained because of this. So notice this. If we want to get 99% charge, well, what we could do is this. We could do VCT, we don't know what it is, we're looking for it, is equal to 99% charge. 99% charge. Well, 99% charge is 0.99 Vmax, and this is equal to Vmax, and then we do 1 minus e to the minus t over RC. So now in this case, well, Vmax and Vmax is canceled, and I end up with 0.99 equals to 1 minus e to the minus t over RC. Change the orders, put this one on the left, bring this one on the right, and what I'll get is this. I'll get e to the minus t over RC equals to 1 minus 0.99. So what is 1 minus 0.99? Well, this is 0.01, or if you will, it's just 1 over 100. 1 over 100. And we have this. So let me just make some space so we could continue the demonstration of why this is true and where this 5 tau comes. So let me just erase all this. Okay. So we end up with this. E to the minus t over RC is equal to 1 over 100. Let me then just also erase this part so we're not fully distracted by it. And then let's see what we get. Well, now we could take the ln on both sides. And if we do take the ln on both sides, we'll be left with minus t over RC equals to ln of 100 to the minus 1, which is minus ln of 100. And well, what is ln of 100 is 10 to the 2, so we could also write it as ln of 10 to the power 2, and you could take the 2 outside as well. You could put it in here, so it will be minus 2 ln of 10, and we have a minus, so the minus and the minus can be canceled, right? So this minus is canceled, so we in fact will get T is equal to 2. RC can also be replaced by tau, so this is the tau ladder. So T is in fact equals to 2 tau ln of 10. So maybe I should just rearrange this a bit better. So this is in fact equals to 2 ln of 10 times tau. And if you do this, you try this with a calculator. So let's try this with a calculator. We do ln of 10. We get 2.3025 times 2, and we get 4.605, roughly 4.605. So this is 6, this is 5 tau. So this is the real value that we should use when we refer to 99% charges. So it's not really 5 tau. The reality is we get 99% charge at 4.605 tau, but we always estimate this as roughly 5 tau. 5 tau is easier to remember. And so this is kind of the common number that people talk about all the time when they refer to capacitor charging, is that you get full capacitor charging at 5 tau, 5 times the time constant, and you get full capacitor discharging at 5 tau. And if you do this here, you could show the same thing, that it is in fact 4.605 tau, not 5 tau, but 5 tau is easier to remember, and that's how we always will use that, because it's easier to do from an engineering point of view. Okay, so I hope this kind of makes some sense to you from an analytical point of view with the equations and the graphing. And now let's see what simulation will show us, and hopefully we have a full circle from concept, from physical understanding, electrical engineering understanding, plotting, equations, analysis, and now we move on to simulation. To simulate the RC circuit, we will use this example here. As highlighted before, we in fact will use 2 different resistors. So one of them will be used for charging, 10 kilo ohm, and we will use a 20 kilo ohm for discharging the capacitor. We'll use a source of 5 volts DC and a capacitor of 100 microfarad. And we're curious to measure and essentially to look at the plot of this voltage here. We could also look at the current, but you get the idea. But in terms of the simulation, we're just going to focus on the plot for the voltage. You could do the same thing for the current. It's going to be very straightforward with Multisim. So just to highlight some stuff, this is 100 microfarad is an actual capacitor. So for example, you could buy an electrolytic capacitor. The price of it is roughly $1 Canadian. Of course, if you buy it in bulk, it's going to be cheaper. And it has a DC voltage rating of 100 volts DC. So if you go beyond that, you could damage this capacitor, and it could also be dangerous. So you really want to stay at 100 volt charging or less. In this case, we're safe. We have a 5 volts source, and it's just a simulation. So there's nothing dangerous or damaging here. We're just running a computer simulation. And that's the advantage of simulation versus actual prototyping or experimentation. Although it's not a full replacement, you still need to prototype and to also experiment with your breadboard as well. So before we simulate, I think it's a good practice to kind of understand the circuit that we have in front of us. So first of all, we realize that we have 2 resistors, which means that we will have 2 speed at which we could charge and discharge the capacitor. Let's figure out some information about this circuit. Well, the charging time constant, we could find it. Let's call it tau C for charging. Well, it's RC, right? So if we're charging, it means that we're looking at the circuit when it is closed this way. So initially the capacitor is fully discharged. It has 0 voltage. We close the switch, current starts flowing, and it will start charging the capacitor. We'll have plus buildup of pluses, plus charge and negative charge on the other side. And the time constant, we could certainly figure it out. We simply need to multiply the value of the resistor, the RC, with the value of the capacitor. So we multiply these two together. The value of the capacitor is 10 kilo ohm, or if you will, 10 times 10 to the 3 ohms. And the value for the capacitors is for the capacitor that we have here, the, let's say, the electrolytic capacitor. It's an actual capacitor that we could actually buy. It has a value of 100 microfarad. Let me just erase this a bit so you can see the what we have here in blue. It's 100 microfarad. So it's 100 times 10 to the minus 6. If we do the multiplication, this becomes 10 to the 4. If we do the multiplication here, well, this is 10 to the 2, and this is 10 to the minus 6. Put them together. These two become 10 to the minus 4. Well, 10 to the minus 4 times 10 to the 4 will get a 1 second. So for charging, we have a time constant of 1 second. What about discharging? Well, when we discharge, well, in that case, we change the switch and we put it to the other side. So when we discharge, we have to put the switch like this. So now that the capacitor is charged, we want to discharge how much power, how much voltage it has, and we will discharge it by releasing the by having a current that flows this way in such a way until all the volts that inside the capacitor is discharged, all the energy inside the capacitor is discharged. It is discharged using this resistor. So how do we find the discharge time constant? Well, we simply need to multiply the resistor, this one, with the capacitor. And if we do that, well, the discharge resistor is 20 kilo ohms, so it's 20 times 10 to the 3. And the capacitor is 100 microfarad, so it's 100 times 10 to the minus 6. We could also figure this out. So this is 2 times 10 to the 4. This is times 10 to the 2, and this is times 10 to the minus 6. This becomes these two guys together becomes minus 4. This is 4. So it all cancels out and we're left with 2 seconds. So this is how we get the time constant for discharging. This is a time constant for charging, the first one. So now that we have this information, we could begin simulating. But I think before doing the simulation, I think it's also useful to know when will we have full charge and when will we have full discharge. So we showed you on the previous slide how we like to use the 5 tau, or in reality we said we could use the 4.605, but let's just use the 5 tau because this is common practice in engineering, is to talk about fully charged capacitor at 5 tau. So if we look at the estimated time to charge a capacitor, well, let's call it TC. It's roughly 5 times the time constant. So we take 5, we multiply it by the 1 second that we got, and this means that it will take roughly 5 seconds to fully charge the capacitor, to fully charge it. So if I have 5 volts, it will take roughly 5 seconds for this capacitor to reach 5 volts. Okay, this is what it means. And if once I have my 5 volts, I want to discharge it. So I have my resistor and I have my capacitor. I have my capacitor like this. This is a 20 kilo ohm. I have a capacitor. I have a 5 volts in here. 5 volts, and I close the switch. So I'm going to start discharging. How long will it take until this capacitor reaches 0 volts? Well, according to this estimate, 5 times tau for discharging, well, it's going to be 2 times 5. It's going to take roughly 10 seconds to fully discharge this capacitor. So these theoretical predictions, these estimate, if you will, are very interesting to do before your simulation because it gives you a sense of what you're expected to have. And now the question is, well, let's just see if this is indeed what we will get. Okay. Now that we've set the stage, we are in fact ready to simulate the RC circuit. So I'm logged into my Multisim, and I hope you could also log into yours. And what we will do is the following. We will grab all that we will need. So we will need a probe to measure the voltage, so we'll need that. We'll need a ground, so we'll put that in here. We will need a DC source, so we will grab that and we'll put it in here. By the way, you could zoom in and zoom out, so I have it zoomed in right now, so you can see these the different components that we're doing, but I could zoom out as well. So we're putting everything that we have some hint that we will need. So the probe, the DC source, the ground. We also need the switch, so we will use the SPDT switch, so we'll put it in here. We also, of course, need a resistor, so we'll need the resistor. We'll put it here. We need, in fact, two resistors, and therefore I could also, instead of grabbing it from the menu, I could also copy it from here. We'll just copy it and it will just paste it here. Let's also make sure that we name everything correctly. So you could double click on it, or in fact, otherwise what you could do is you could just press on it and then press the wheel here on the right, and then this allows you to change the naming of it. So let's call it VS like we have in the simulation, and we want it to have a value of 5 volts, so let's keep that at 5 volts. For the probe, let's just call it, we only will have one probe for voltage, so let's just call it probe. So let's just call it PR. As such, let's just write it in lower r, PR, like this. For the resistor, well, we need one resistor to charge, so that's for charging, RC. We need another resistor to discharge, and that's RD. And of course, I also need to change their values. So for charging, we, as we saw in the example, we said we'll use a 10 kilo ohm. So K is already there. So if with Multisim, if you put K, it takes care of the kilo ohm. So K is already there. I'll just put the 0. So we change it to 10 kilo ohm for the resistor for charging. And for discharging, I need a resistor of 20 kilo ohm. So let's just put 2 and 0. K is there again for kilo ohm. So now I have everything that I want. I have the source of 5 volts. I have the probe to measure the voltage. I have the ground. I have a switch. Maybe we could change its name to just S. Why do we have a 1? We only have one switch, so let's just make it like such. And I think I have all that I need at this point. So, oh, and where is the capacitor? We forgot the capacitor. The capacitor is also the critical element, which we forgot, which is here. Let's grab a capacitor. Let's just call it C, because we don't have more than one capacitor. So instead of C1, let's just call it C. And for the value, well, we said we're going to use a value of 200 microfarad. So you see here with Multisim, there's a mu. Of course, for with your keyboard, if you want to change the value, you could just put the 100. But for mu, you could in fact delete it. Then you'll have 100 farad. But of course, that doesn't make sense. You want microfarads. For micro, you just enter the letter U, and it will change to mu here. So it knows that when you enter U, you actually mean a mu for capacitor. So that's also nice from Multisim that they made it accessible in that sense. So now we have all the components that we want, and at this stage what we need to do is essentially just connect everything together. For the source, I don't necessarily like to use this one, so I'm going to change its symbol. You could, you have a variety of symbols that you could use. This is a variable, and I like this one here with a circular with a plus or minus. It's more consistent with what we've used in class notes and so on. So I'm going to change it to that. And I think we're almost ready. So let's just assemble everything together. We have a source, so let me just put it in here. We have the charging capacitor, resistor rather. Let's just put it maybe here. We have the discharging. You could flip the order like this. So if you switch it like this, it changes the orientation of it. So we flipped it by 90 degrees. We could also flip the capacitor as well. Let's just put it somewhere maybe here. Maybe we need to put everything kind of spaced out so that it looks nice when we put the wiring. We also need to have our switch. So the switch, the way we will do it is maybe we'll do. Let me just see. So something like this. So we'll set it up like this. Maybe push this a bit here. Okay, and don't forget, I think everything, as an engineer, you should learn to make everything aesthetically appealing, and also it should be the wiring should be clean, everything should be nice, so that when you do, somebody will look at your report, they will be able to understand what's going on in an easy way. So we have the ground, and we have the switch, we have this, we also have the probe to measure voltage. We'll put it at the end. Now let's just connect the wires. So to connect, I think everything is properly sized. So by the way, you can scroll with your mouse to zoom in and zoom out. So I think this is not something very difficult to do. So I'm going to just zoom in so you can see how we do the wiring. We just click on it on this node of the source, and then we go to the next source that we want to click. You'll see these circles that are coming in, which means that I have a connection. I could click on it, and then I form the connection. Now there's this label here, 1. We could remove these net labels. I don't necessarily like these net labels, so we could just remove them. We could just click on the wire and then remove them. They're a bit distracting, so we could get them out of the way. And let's connect everything else. Let's connect the charging resistor to the switch. So we have this like this. We could also remove its net label. What else do we have? Well, we have the discharging resistor. We could also connect it to this switch here. And again, we could just remove the net labels at the end. Let's just connect everything. We have the switch now connected like this to the capacitor. So we have this. We also have the DC source connected to the ground here. Let's put it like this. We could then connect the capacitor to this common ground, and also the discharging resistor as well. So now we have all the connection that we want. This should be similar to what we have in our in on what I showed you before, the theoretical schematics that we have. We could just adjust it, maybe bring everything a bit closer, properly aligned. Everything seems a bit nicer like this. So it's a bit also compact. Let's just remove these labels because they're not that nice, so that it looks a bit less crowded with information, and we only keep the useful information for us. So now I think we have everything ready. We're missing the key part, which is the probe to measure voltage. So you want to measure the voltage across the capacitor. So we could just put the probe here. Because when you measure voltage, you always want to, essentially voltage, it's always with respect to 2 points. So you could grab the minus from the probe and you could put it here. So this means that you're measuring the potential difference. But in this case, I don't need to do that because I have the common ground. So if I just put a voltage probe here, it knows automatically that I'm measuring it with respect to the ground. So that takes care of this. So at this point, we have the circuit. It seems like we have everything set up. Let's just maybe bring this a bit closer so it looks less spaced out. Maybe this as well, a bit closer so it's less spaced out. Let's put the probe as well. So we have everything set. So now that the circuit is ready, you may perhaps try to change the switch. Well, this will not work at this point. You need to run the simulation. So if we run the simulation, how do you run the simulation? Well, you press the play button here to run the simulation. Let's just do it. At this point, the capacitor is discharged. So we expect the voltage to remain very small. So let's just run it. Let's see what we see. And we see 999.70 microvolts. So that's roughly 1,000 microvolt. Well, 1,000 is 10 to the minus 3 micro. So this is essentially, it's 10 to the 3 times 10 to the minus 6. So this is essentially 1 millivolt. And because it is 1 millivolt, it's basically, for us, it's equivalent to 0 volts. Okay, so the switch is like this. If I change the switch, I click on it, I click on the switch here, and then suddenly current will start flowing and the capacitor will start charging. And if we leave it long enough, it will start charging until it reaches 5 volts. So let's do that. Let's click on the switch, and then notice that the capacitor starts charging. I hope you can see this. I think when I zoom out, it becomes reasonably sized. So notice that it's going up, and the timer is moving until it reaches the value of the maximum value of 5 volts. So it's never going to get to 5 volts. We need to go up until infinity. So we saw that from the equations. But if we consider 5 tau in terms of time to let it fully charge, well, it will get us to this value. So we gave it enough time to charge to 4.9995 volts, which is very close to 5 volts. If I close the switch again, we also need some time to fully discharge it. So to discharge it, we want to be somewhere in the millivolts. So let's change the switch. So I'm going to change the switch. Let's close it. And then notice that you're discharging the capacitor. You're discharging, and notice the time, how much time it's needed to discharge until we reach millivolts. So it discharges, it goes all the way. We need some time. We need to give it the necessary time to discharge. Now we saw from the analysis previously, we estimated we need roughly 5 seconds to charge the capacitor, and we need roughly 10 seconds to discharge the capacitor. So let's see what happens here. So it's still discharging. It's still very tiny here. This is millivolts, right? So it's still very small. And in fact, we need to let it run a lot more, maybe a bit more to discharge more, but it's already in the millivolts. So for us, for all practical purposes, this is essentially just 0 volts. This is very small voltage at this point. Okay, so I'm going to stop the simulation. And if you run the simulation again, well, in this case, it begins at 0. So if your switch is at the discharge, you begin with a fully discharged capacitor. And for us, we said fully discharged capacitor by default, which you have here, is 999.7 microvolts. So this is roughly 1,000 micro. Micro is 10 to the minus 6. This is 1,000. So this is essentially 10 to the minus 6 times 10 to the 3. So that becomes 10 to the minus 3 volts. So this is basically 1 millivolts. So 1 millivolt is by default a discharged capacitor. This is what we have. So now on top, you could graph what's going on. So you have a grapher here. So it allows you to graph to see what's going on in terms of what happens as time moves. How does the voltage changes? And in fact, you have just a grapher by itself. This is the schematic by itself. And you have a split view. You have the schematic and the grapher. So you have both. And maybe this is the best way to have both of them, the schematic, so you could change the switch and then see what happens in here. And you could, of course, resize your screen a bit. We don't need all this information. We can see it. We just need to move here. And then the rest, we could just see what happens. Now, let's just make sure that we have all the proper settings. So I'm going to just press on the wheel just to make sure that we have the proper settings for the grapher. We could put it for the trigger to none. That's fine. You could put it to rising, fall, or either. Let's just put it to either. What else do we need? For the probes, for the cursors, not the probes, but rather for the cursors, we'll do that at the end. Once we have a nice plot, we'll do that at the end. For the time, well, we need to run it enough time, right? So we said that we'll need some 10 seconds to run, maybe a bit more. So we could just set it up from 0 time to, I don't know, maybe 15 seconds, something like that, because we said that we'll need 5 seconds to charge and then 15 seconds to discharge. So let's just put 10. In fact, this will be changed when we do the simulation. For the voltage, the minimum voltage that we want is a very small voltage. Let's put 0. Here they have 900 micro. Let's just put 0 volts. 0 volts, the minimum voltage. And for the maximum, well, we have a source. If you see here, we have a source of 5 volts. So we could, in principle, let's go back here. We could, in principle, change it to 5 volts. But in order to have a nice view so that we see what's going on, let's add it by an extra 1. Let's do 6 so that we can see a nice plot for 5. So 5 is expected to be somewhere here. 6 is 1 voltage beyond that. So we know we're not going to be here, but it's going to be nicer when we plot. So I think we're all set up here. Let's just run the simulation. Let's run the simulation. I think we're ready. Let's just run the simulation. Let's see what happens. And by the way, so let's just close this. And by the way, I left it at 1, maybe here. You see here, this is the division. So we have micro. Let me just change it to 1 second. 1 second per division. Let's do it to 1 second per division. You see here at the bottom, 1 second per division. Here, 1 second per division. You want to keep it at that. I think that's reasonable. Where did I get the 1 second per division? It's always good practice to take some of the value from time constant and to put it to set it to that. So we have a time constant for charging of 1 second, and we have a time constant for discharging at 2 seconds. So I use the smaller value of 1 second. And I think this is reasonable to see what's going on. So I'm going to stop the simulation. I'm going to run it again. So let's just see how it looks like. Let's see how it looks like. 1 second per division. And I'm going to change the switch. So notice what I'm going to do. I'm going to change the switch. I'm going to toggle it. So notice what happens. Let's just close this side so you have enough information. And notice what happens. It starts building up. It starts building up. So we wanted to give it enough time to charge. And it will reach full charge when it reaches 5 volts. Enough time to charge. 5 volts. Okay. Let's keep it a bit on the 5 volts. Let's keep it a bit on the 5 volts. A bit more. A bit more. Okay, now let's just change it. Let's change it. Now we're discharging. Notice that the curve is discharging. And it's going to discharge at a different rate. It will take different time to discharge. Notice how it discharges. And the capacitor discharges, and we're hoping that it reaches somewhere close to the 0 line. So the capacitor is discharging. Let's give it some time. And of course, there's a timer here, but that's fine. We don't care too much about this timer. We will use cursors to measure time. Let's give it a bit more time. When we think visually it looks close to the 0 line. Okay, now I guess let's wait a bit more. I guess we could stop here. We could stop here. And in fact, you could keep going with the charging and discharging as you wish. So let me now just put the grapher. Let me just put the grapher. And let me just, let's just move things around so you can move the plot that you got. So we got the charging here. So we let it charge. This is what we got for the plot. And as you notice, we also let it discharge as well. So the discharging of the capacitor is also here. By the way, you could change the time frame. You could scroll. You could change the time frame. So to do that, you could zoom in, zoom out. You could change the time frame as you wish, and it allows you to do measurement accordingly. At this point, what we want to do is we want to use cursors. So I'm going to press the wheel here, and I'm going to use cursors. Let me use the cursor 1. I'm going to use the X cursors because that's what we're interested by. So I want to know how much time it took to charge. So what I'll do is I'm going to put it here. I'm going to put it at this value, and I'm going to look at, by the way, let's just maybe zoom out a bit. Let's just move it a bit. 1 here, and then let's put C2 maybe somewhere in this neighborhood. Maybe you cannot see fully at the bottom, but if you, because it's the screen capture is cutting it a bit here, but if you notice that it is very, very close, so it's roughly in this neighborhood. It's about what, 5.7 maybe. So if we do something like this, we get a bit closer. It's the time that it took to charge. If you look at the time that it took to charge, this delta X is about 5.3 seconds. 5.3 seconds. This is how much we see that it needs for charging the capacitor. And what we estimated earlier was 5 seconds. So that's a very nice estimate that we got earlier. Let's move this along. Let's see how it looks like with discharging. The discharging of the capacitor. We expect 10 seconds. Let's see if this is indeed true. So let's put C1 here. Let's put C2 in here. And if you notice, maybe a bit more, we notice that we have a discharging of 10.7 seconds. 10.7 seconds, that's what we see. We could also adjust it a bit more, maybe in here. So 10.7 seconds, that's kind of reasonable what we expected. We expected 10 seconds to discharge, and this is also reasonable. So this is great. So what we got from analysis gave us exactly what we got from simulation. Now let me just go back to the schematic. Let's just put the split view here, and let me just run the simulation again. Let's just run the simulation again. Let's just, so again, we start at 0. We have 1 seconds per division. Let me toggle it so it should go up. It should go up. By the way, I could stop anytime. I don't need to wait until 5. Let me just change it. I could go down, discharge it right away. I could just go up, charge it again. So you could play with this. You could play with this. And these small graphs that you have, you could also represent them with the equations. So remember when I told you Vmax? You could decide when to stop charging and when to start charging. You could toggle it whenever you want, right? You don't need to wait until it reaches the maximum value. You could stop it whenever you want, right? So discharge, well, suddenly I change my mind. I want to charge. I charge, and then suddenly I want to discharge. I could just let it down, discharge a bit more. And now I'll just, I said, okay, fine. Let me just charge it back again to full value. So let me just wait until it reaches its full value of 5 volts. So you could do that. And the equations are fully compatible with these, what you see in front of you from what I showed you earlier. Okay, so that's it. This completes what I wanted to show you for this. Thank you for your attention, and I hope this was helpful. If it is helpful, please maybe press the like button. This will help other people also benefit from this. Thank you for your attention.